Welcome back to the ML Boost channel. You know from the previous video that this playlist is about reliable forecasting, and the first element in assessing reliability of any forecasting method is measuring the performance of the forecasts on unseen data by a proper error metric. I call this the first element in the sense that if the performance on unseen data is not good or is not measured using a proper error metric, then you should send the forecast home instead of relying on it. This video is the continuation of the same topic, and here we are going to learn about another evaluation metric. In the previous video, I showed that one of the problems with MAPE is that it's not invariant to the actual forecast interchange. What that means is that if you interchange the actual and forecasted values, VT hat and VT, MAPE will change, which results in a problem with MAPE that for a given amount of absolute error, the MAPE of an over-forecast will be higher than its under-forecasted counterpart. For example, in this table, you can see that when we interchange the actual and forecasted values, the over-forecasted case, that is, the case with positive error, has higher MAPE than its under-forecasted counterpart. To tackle this problem of MAPE, an error metric originally called adjusted-MAPE was introduced with a definition similar to MAPE, except that in the denominator, instead of the actual value alone, it uses the mean of actual and forecasted values. The problem with this original definition is that it can be negative, so its denominator was later modified to contain the mean absolute values. With this modified definition, adjusted MAPE is obviously never negative. Now, let's recall the earlier example that showed how the value of MAPE changes when we interchange forecasted and actual values. If we calculate and add adjusted MAPE to the same table, you can see that its value does not change with the interchange. In other words, adjusted MAPE is invariant to actual forecast interchange. This is why sometimes adjusted MAPE is referred to as symmetric MAPE, but one needs to be cautious with the term symmetry, and for a very good reason, there has been some pushback against calling adjusted MAPE symmetric. For example, in this paper. Imagine that in our table, we get the over-forecasted column not by interchanging actual and forecasted values, but by changing the sign of the error while keeping the actual value and absolute error the same. In this scenario, it is the MAPE that remains the same, while adjusted MAPE changes and puts a lower penalty on the over-forecasted case. This shows that adjusted MAPE can in fact be asymmetric, depending on how you define symmetry. Therefore, I believe, like the authors of the paper I showed earlier, the term symmetric MAPE should not be used. The other thing about this adjusted MAPE is that its value is always below 200%. That is because the term inside the summation is always less than 1. Averaging values that are less than 1 and multiplying them with the prefactor results in an adjusted MAPE that is always below 200%. This is in contrast to the original MAPE, which can be arbitrarily high. This results in the behavior of these two metrics to be very different when it comes to outliers. To investigate this, let's consider a simple example where we have 3 true values shown by the 3 circles in the graph that all fall onto the blue line. Let's also imagine that our first set of forecasts, shown by the colored circles here, lie perfectly on the true values. In other words, they have no errors. Note that the forecast at t equal to 0 has a different color, red, than the 2 other forecasts, yellow. That is because we are going to do something special with it. We are going to handle it as an outlier by increasing its value away from the corresponding true value, so that we can see how MAPE and adjusted MAPE respond to outliers. On the right, we will have a plot that will show two curves, a green curve representing MAPE and the blue one representing adjusted MAPE, as functions of the error of the outlier point, that is, the distance between the red circle in the left plot and the corresponding true value at t equal to 0, denoted by E sub outlier. Now pay attention to how in the right plot MAPE and adjusted MAPE vary as the red circle in the left plot, our outlier, moves away from the true value. Let me play the animation again. So what happens is that as the error of the outlier point increases, MAPE keeps increasing linearly. Adjusted MAPE, however, increases initially, but then it converges to somewhere around 64%. In other words, the maximum amount that a single outlier can contribute to adjusted MAPE is capped. No matter how large the error of the outlier is, its contribution will not exceed a specific value. To further investigate the sensitivity of adjusted MAPE to outliers, let's look at its equation one more time. Let's imagine that we have a single outlier point and denoted with I sub out. The question that we are interested in is, what is the maximum amount that a single outlier point can contribute to the overall error? What we are going to do is to decompose the right-hand side of the equation into two parts. The first part shows the contribution of the outlier point to the overall error, and the second part shows the contribution of all the other points. Because we are interested in the contribution of the outlier point only, we can drop the second term and simply write that the contribution is equal to the remaining term. Now, because we are seeking the maximum contribution of the outlier point, we can let the forecast at that point to go to infinity. In that limit, the numerator and denominator of the term enclosed by the bracket will be both v hat, so the entire term, that is the contribution, will converge to 200% over h, the number of individual forecasts within the horizon. The takeaway point is that with adjusted MAPE, the contribution of a single point, for example, an outlier, to the overall metric is capped at an amount that is inversely proportional to the forecast horizon. With MAPE, however, that contribution is unlimited. This whole thing results in adjusted MAPE being much less sensitive to outliers than MAPE. In summary, when you want to decide between MAPE and its cousin adjusted MAPE, you have to think about the real-life penalty of forecast errors, the invariance that the penalty has, and the outliers. If the penalty is invariant to actual-forecast interchange, adjusted MAPE should be used. If it's invariant to the error sign, MAPE should be used. As far as outliers are concerned, if the negative impact of having an extremely bad outlier on the penalty is limited, adjusted MAPE should be used. If the impact is unlimited, MAPE should be preferred. For those of you who made it this far, thank you for watching this video. If you have any comments, feel free to let me know in the comments section. Hope to see you next time.